This video will be about the discriminant and modeling data. So when you are working with the discriminant is part of the quadratic formula. So the full quadratic formula is the negative b plus or minus square root of b squared minus 4ac all over 2a. So that's the full quadratic formula, but the discriminant is just the b squared minus 4ac part. So whereas the quadratic formula will actually tell you the answers and the roots where you cross the x-axis, the discriminant is just going to tell you how many answers can you expect. So there are three possibilities. Our first is that you would have a quadratic that crosses 2 times. Crosses our x-axis twice, so that means you have 2 answers. Our second possibility is that we just touch the x-axis once with the very bottom, or the quadratic can be flipped upside down at the very top. If you just touch once, then you have 1 answer. And our third possibility is that we never cross the x-axis. Again, on any of these, you could be going upside down. The quadratic doesn't just have to be right side up. So if you never cross the x-axis, there are no answers. So 0 answers or no answers. Sometimes they write it a little bit differently and they take the actual discriminant formula, b squared minus 4ac, and for 2 answers, what happens is that discriminant ends up being positive. It's bigger than 0. So positive discriminant means our 2 answers. Sometimes they'll write it just as the formula b squared minus 4ac. Maybe they'll say b squared minus 4ac equals 7. 7 is greater than 0, therefore you have 2 answers. For one solution, our discriminant is 0. And if our discriminant is negative, so less than 0, that's when we have the no answers. So instead of actually getting the picture, if we just find this discriminant, we can decide, do we have 2 answers, 1 answer, or no answers. So let's say we have 2x squared minus 3x minus 7 equals 0. We know the formula is b squared minus 4ac, but what is a, b, and c? Well, they go in order by the variable with its exponent. X squared always should come first, and that is a, so a equals 2. X should come next, and the number next to it, the coefficient, is -3, so b is negative. The last number is -7, so c would be -7. Now that we know each of these, we plug them into the formula. So where I see the letter b, I'm going to replace that with -3. Now we still had squared, we still had -4, then we're going to replace a with 2 and c with -7. We're going to simplify this. So to simplify, -3 squared, -3 times -3 is +9. -4 times 7, sorry, I jumped. -4 times 2 is -8. You have to do multiplication before you do any more subtraction, so -8 times -7 is +56. And then adding together, 9 plus 56 is 65. So this number is a positive number. That means we know we have 2 solutions to our quadratic. We could use the full quadratic formula to find the 2 solutions, but if they just ask how many solutions, we would stop there. So also in this section is modeling data. So there are 3 main ways that we're going to learn to model data. These are not the only ways to model data, it's just the three we are learning. They're the three basic ways. Linear is y equals mx plus b, and that is a straight line. Could also have been going from top left to bottom right. Quadratic, we just worked on discriminants with quadratic. For modeling data, we have y equals ax squared plus bx plus c. We know it's a quadratic because it has the x squared term, whereas linear only has a plain x. And a quadratic looks like that U shape, also called a parabola. And we have exponential. In real life, exponential is used a lot for population growth or interest in banking and loans. So exponential looks like this, y equals a times b to the x. This time our variable is an exponent. And exponential looks like it's just going to follow along on a straight line until it suddenly goes up. So if they give us a set of data, they want us to figure out which of these models works best. The first way to do that is to just draw a picture. So if we have the data -1, 1, 0, 0, 1, 1, 2, 4, we can draw our coordinate system. We have a point at -1, +1, at 0, 0, at +1, +1, and at +2, +4. So then we just decide, well, which one does this look the most like? If we just looked at these 3 points, we could think, well, maybe it's exponential. It's going up pretty quickly. But this last point here makes it make a sudden turn back up instead of falling straight down. So the best fit for this one would be a quadratic function. So we solved this one by actually graphing it. You can also check using a table. Let's say we have -1, 1, those same points from last time, but this time they're in table format. So on the left side, if these three models are going to be working out, we should be going up or down by the same amount. So from -1 to 0, I added 1. And from 0 to get to 1, I add 1. From 1 to get to 2, I add 1. So we're adding the same amount every time. On the right side is really where it's going to tell us if we're linear, quadratic, or exponential. On the right side, we're going to try the same thing. Well, to get from 1 to 0, I minus 1. To get from 0 to 1, I add 1. And to get from 1 to 4, I add 3. These did not match up. If this first time you check they do match up, then it's linear. So if this had been, +2, +2, +2, this would be linear. If it's not linear, we do one more level and check what's the difference between these. So from -1 to 1, I have to add 2. From 1 to 3, I also add 2. This time we are matching. When the second level matches, this is a quadratic. So if the first level had matched, it'd be linear. If the second level matches, it's quadratic. What if neither of them match? Well, if neither of them match, then it's probably exponential. When you're checking exponential, instead of checking how much you add by every time, you'd be trying to find how much you multiply by every time. And we'll see an example of that in a minute. Let's do one more example of a table. Let's make a new table. And this time we're going to take it one step further. We're not only going to decide if it's going to be quadratic linear or exponential, we're also going to write the equation for it. So these should be going up by the same amount every time. We're going up by 1 every time. So that's okay. We check on the right side. Sorry, this should have been negative 0.5. 0 to negative 0.5. I am minusing 0.5. Negative 0.5 to negative 2, I'm minusing 1.5. Negative 2 to negative 4.5, I'm minusing 2.5. And negative 4.5 to negative 8, I'm minusing 3.5. If you have trouble doing that in your head, you can also go backwards. So if I want to figure out, well, how much am I changing by to get from negative 0.5 to negative 2? I'm just going to minus them. Negative 2 minus negative 0.5 is negative 1.5. So that's a second way you can find these values. So then we check the next row. These did not match, so it's not linear. Negative 0.5, to get from that to negative 1.5, I minus 1. Negative 1.5 to negative 2.5, I minus 1 again. And negative 2.5 to negative 3.5, I minus 1 again. These do match, making this a quadratic. We know the equation for a quadratic was y equals ax squared plus bx plus c. Now that is a difficult one to find the equation for, but we do have something that makes it easier. When you have the point 0, 0, you can shorten this and only use the y equals ax squared. So we're not going to use the rest of this to find the equation, just the y equals ax squared. So really we just need this letter a. So this letter a, you determine it by plugging in one of the values. I'm going to pick one at random. I'm going to pick 2, negative 2. We know 2 is our x value, negative 2 is our y value, so we have negative 2 for y, a times positive 2 for x, and we're going to solve for the letter a. 2 squared is 4. Divide both sides by 4. Negative 2 divided by 4 I can simplify. That would reduce to negative 1/2, because negative 2 can divide by 2 and make negative 1. 4 can divide by 2 and make 2. So we have a equals negative 1/2, and now we can write out the equation as y equals negative 1/2 x squared. If you're unsure if you did it correctly or not, you could check your work. You could plug in a point and see if it comes out with the correct y value. But you do not have to check your work if you do not want to. So let's apply this to a real-world problem. Let's say you are studying frogs that live in a nearby wetland area. The following data was collected by a local conservation organization. They indicate the number of frogs estimated to be living in the wetland area over a 5-year period. Determine which kind of function best models the data, and also write an equation for the data. So where this says estimated population, our answers may not be quite as clear-cut as on some of our other examples. We might only find that our answers are close to each other instead of matching exactly. But we're still going to follow that same process. We would say, okay, and we always double check. This adds by 1 every time, so the left side is okay. We're adding by the same amount every time. So adding or subtracting 120, I would have to minus 19 to get down to 101. 101, I'd have to minus 15 to get down to 86. 86, I'd have to minus 14, and 72, I'd have to minus 12 to get down to 60. So these aren't close enough, even though this is an estimation, so we may not match exactly. Those are some pretty big jumps. Negative 19, negative 12, those aren't very close together. So we're going to check for quadratic. It was not linear, so we move on to quadratic. So for quadratic, Let's see, from negative 19 to get to negative 15, I would have to add 4. From negative 15 to negative 14, I'd have to add 1. And from negative 14 to negative 12, I'd have to add 2. Again, these are not very close to each other. So even though, again, this was estimated, this probably is not correct. So let's see a exponential one then. Linear didn't work, quadratic didn't work. Let's try exponential. So exponential, we're trying to figure out what would we have to multiply by. Now this is not clear-cut at all. I don't know what I multiply 120 by to make 101. So I'm going to just do the opposite to figure it out. I'm going to do 101 divided by 120. Notice I went in the opposite order. 101 divided by 120, if you plug it into a calculator, is 0.842. It keeps going. We're just going to use 2 decimal places, 0.84. So now I try the next one. Again, I don't have any clue what I multiply 101 by to make 86, so I'm going to go backwards. 86 divided by 101. If I plug that into a calculator, I get 0.851, so 0.85. Same thing on the next one, 72 divided by 86. We give you 0.837, so that rounds to 0.84. And 60 divided by 72 would be 0.833, so 0.83. So these are pretty close to each other. They're all in the 0.8 range and just barely, 0.83, 0.84, 0.85. They're right next to each other. So these are exponential. We are matching. Since it is an estimation, we do want to average these out. If we added them all together and divide by 4, it would come out to 0.84. So we know this is exponential. We know the equation for exponential is y equals a times b to the x. So in this equation, a is considered the initial value, and b is your amount of change. So with quadratic, we had to plug stuff in to y and x to find a. For exponential, we just have to identify what is what. So initial value is the value that goes with 0, where x is 0, y is 120. So that is what we put in for a. A is 120. B is that amount of change. Well, just to find if it's exponential, we found our amount of change. We averaged it out. It was 0.84. And sometimes they'd put this in parentheses. So that would give us our equation. So let's do one more example because we haven't seen a linear equation come up. Say we have the points -3, 2, -2, -1, -1, -4, 0, -7. So if I put it in table format, because that's a little bit easier to figure out which one is which, you can line it up and see easily what's the amount of change each time. We're still adding by 1 every time on the left. On the right, let's see, to get from 2 to -1, it's a little more difficult, so I'm just going to do the backwards. -2 minus 1 is -3. So I'd have to do 2 minus 3 to get to -1. -4 minus -1. Negative is really plus, is also -3. And -4 to -7 is also -3. So the first one's matched. This is linear. Linear we know is y equals mx plus b. And when writing the equation, it is more like your exponential equations. You just need to identify what goes where. So in this case, m is your amount of change, which again, just by identifying, we already know what that is, -3. And b is your initial value, so 0 has -7 with it, so -7. So exponential and linear equations will act more similar when you actually make the equation. You just identify the amount of change and you identify the initial value to plug in. Quadratic, you have to actually plug in an x and a y value to figure out that coefficient in front. And then originally we talked about the discriminant. When the discriminant is positive, you have two solutions. When discriminant is 0, you have one solution. And when discriminant is negative, you have no solutions. So that concludes our discussion on discriminant and modeling data.